Hi, welcome to my video on game theory problem I have observed in real life. Today we'll focus on the matter of train tickets. Let's imagine a situation in which we want to get from Sellyog to New Street Station. In order to do this, we can buy a ticket or not, or decide to cheat and not buy it. It is a normal form game consisting of two players, the passenger and railway company. Each player has two actions. Passenger can get a ticket or not, and railway company can check the tickets or not. Now, payoffs of different actions can be presented with views of prices for tickets and penalties for not. Here we can see the payoff matrix. The price of a ticket is 240, penalty is 20, and I have also used the parameter P in case of payoffs for passenger when buying a ticket and having it checked. I decided to use it as you get a slightly higher payoff when the ticket is checked. As you know, you couldn't avoid paying for the ticket, but you could get fined if you didn't have it. So P can take the values between 0 and 17.6. As in this situation, you weren't supposed to get a ticket, but you have it, so you avoided paying 20 quid. So we can see the actions, passenger is red, and the railway network is black. To solve this game, we need to find the Nash equilibrium. We can do this by using the dominant strategy iteration. Payoffs for railway network are higher in case when they check the ticket, and that is their dominant strategy. As they're indifferent between 240 and 240, but they would rather have 20 than minus 2.4. Hence, having eliminated the action, we know the passenger has higher payoff when he buys a ticket, so we end up at check and buy. Now let's calculate Nash equilibrium. So let's assume probability of being checked is Q and probability of buying a ticket is X. After calculations, I have found out that X is equal to 1, so passenger should always be to buy a ticket, as prices and penalties are constructed in a way you cannot beat the system. Now they're gonna check with the probability Q equals P plus 20 divided by 22.4 plus P. So depending on personal preferences, the value changes. It's gonna be Q most of the times because passenger will always want to get a ticket. Now, if we know the dominant strategy and mixed equilibrium, why not always check? Because of the cost of personnel, which is included in matrix as C. Those are incentives not to check at slower times and less busy stations. So I have calculated that cost of hiring personnel would have to be bigger than 0 per ticket if everyone had a ticket, and bigger than 22.4 when not having a ticket for the tickets not to be checked. Why not always buy a ticket? Because we know that this actually happens. Those incentives come from the fact that there is a probability of not being checked and saving money. So I've calculated what the probability of being checked has to be in order for passenger to always get a ticket. And I have found that X is bigger than P divided by P plus 17.6. As it depends on P, even when P is biggest, the highest incentives to cheat. The rate of tickets being checked is less than 50%. So, lessons to remember: buyer tickets, prices, and penalties are designed in a way you cannot win. Tickets are not always checked because of extra cost in lower rush and smaller stations. P could describe the propensity to cheat of a passenger. Thank you for your time and watching my video.